I know this is the last session, so I'll try and make it as fun as possible and try and take you through the ride of what metal organic frameworks are and talking about two very specific areas, which is energy storage and biomedical applications. I'm not going to go into deep diving about research about them, but what I'm going to try and present to you is the approaches by which we can try and use MOFs for such kind of applications. So my presentation will follow this particular outline where I'll just introduce MOFs to everyone. I'm sure some of you might not have known much about it, so this would be a good chance to learn about MOFs. Of course, they're popular since October this year because they won the Nobel Prize of Chemistry. So I'll touch upon the Nobel Prize aspect very briefly, and then I'll talk about the two application areas. The first one is going to be our energy storage devices, where I won't talk directly in terms of how energy storage is important or how MOFs are important for that. But what I'll do is I'll talk about green synthesis and azo-functionalized MOFs. And the latter part is going to be about biomedical applications. And in this particular case, I'm going to talk about how to use MOFs to tackle viruses. And with viruses, you'll see what comes up next. So I'll start with this particular image on this slide, which is the same image that the Nobel Prize website, nobelprize.org, had when they announced the Nobel Prize for chemistry this year. And what they wanted to show with this image for a layman or someone who doesn't understand MOFs are, is that this is particular like a place of residence. It's empty inside. It's got doors and windows. People and guests can come inside. They can spend time. They can reside there, and then they can leave. You can imagine a MOF to be something like this. It's a empty. It's got a structure. It's got an empty space in between. Gas molecules go inside. They can be used for catalysis. They can be used for something else, and then they can come out once their purpose is finished. So, kind of remember this image as we go along the slides because this will come in handy wherever it's needed. In terms of more chemistry intuition or understanding what basic ideas about MOFs are, the name is very, very intuitive. It has to have a metal ion, it has to have an organic ligand, it has to have a guest molecule. It doesn't necessarily need to have a guest molecule, but because the synthesis is carried out in the presence of solvents, typically using hydrothermal or solvothermal synthesis, the guest molecules typically occupy this empty space that forms during the structure. You would ask whether you can pick any metal ion, any organic ligand, and you end up getting a structure. Well, you might get, but this is not the case for most of the morph systems. The key thing here is the metal ion has a specific coordination geometry. Go back to your inorganic classes. Remember that each cation has a specific direction for coordination, so it cannot be completely random. The organic part itself also cannot be completely random. So the donor groups have to have a specific geometry. In this particular example, which is linear, the donor groups are assumed to be 180 degrees apart, but it has to have some kind of symmetry. And as I show you some of the examples, you'll appreciate this idea a bit more. So once you have got two symmetric building units, they essentially form this kind of a small building unit. But this is not the end of it. They actually end up propagating along 1, 2, 3 dimensions, and you end up getting a structure that looks like something like this. It's got a long range periodicity, it's got porosity, it's got some form of channels inside it. And what are the key benefits of forming these architectures? Of course, you end up getting a lot of porosity, but the more important thing is because of the long range periodicity, you end up getting these structures as very crystalline materials. And why crystallinity is important, I'm sure over the next 5 days, all of you will be experts in this or already know something about it. Is once you have crystallinity, you can actually apply structure property correlationships in any application. So having a crystalline structure is a big, big benefit for these materials. And of course, because we are using an organic part, we are using a metal ion, we actually can tune the chemical and the physical properties of both the building units and the eventual structure that forms. So, for example, if you have got a fluorescent organic ligand, you can assign fluorescent properties to the morph that forms. If you have got iron as the metal center, you can apply magnetic properties to the morph that forms. So, depending upon what physical and chemical properties the building units carry, the eventual structure will also have the same features. So, if you're not kind of still familiar with this idea of how morphs look like, just go around on the streets, look at a construction site, you'll always find something like this. So this is a scaffolding arrangement that all of us see everywhere, right? So if you're looking at a scaffolding arrangement, just look at it in slightly different way. Look at the rods, vertical or the horizontal ones. They can be thought of as the organic ligand, and the point at which or the nodes at which they connect to each other would be the metal ions. So essentially, a scaffolding arrangement has got a lot of empty space in because it don't need that space, but they're kind of rigid and well connected to each other so that they form this long range architecture. So I've shown a football stadium after the scaffolding arrangement, and there's a very big reason for it. I've been saying that morphs have porosity. The idea of porosity in these structures is very, very important. But how much porosity is there in these structures? So just to give an idea, can someone tell me the football playing area or the playing area of a football field? Any number, any guess in terms of meter square? Anyone? I'm sure everyone has seen a football field. 2000 meters square. Any other answers? No? Okay, so FIFA qualifies for a football stadium to be professionally played. It has to have a dimension of 70 meters by 100 meters. So roughly you end up getting something which is 7,100 meters square. To encapsulate this idea of how porous morphs are, this particular morph, which is an example called as DUT60, you don't have to worry about the nomenclature at the moment, but this particular morph has an internal pore surface area of 7,800 meters square per gram of material. So the surface area of this entire football field is now trapped in 1 gram of this particular morph material. And to understand what 1 gram is, I think all of us know what 1 gram is, but just to appreciate this idea, a lot of us had tea and coffee just now, and we added some sugar there. We didn't have sugar sachets, but if you go to a shop outside, you'll find sugar sachets. So each of these sugar sachets typically are made of 5 grams. So 1/5 of this weight of this material will contain the surface area that's equivalent to one football field. So that is kind of this idea of porosity in these materials. And of course, not every morph is this porous, but this is kind of stretching the limit and showing you that a stable metal organic framework can contain this much surface areas. Porosity is how much? 90%? Porosity is, yeah, it could be up to 90% as well. I'll come upon the density part as well. Yeah. So in terms of if you're still kind of now getting into this idea of what morphs are, let's go into a bit more chemical intuition. So all of us have done basic inorganic chemistry, and we have come across these examples where our teachers draw on the board and show that how coordination works when a carboxylate group binds to a metal ion and it forms this paddle wheel unit. We have this paddle wheel unit for zinc, we have this for copper, different examples. So what people thought who were working on morphs is, why do we limit ourselves to this particular unit? Instead of this R group, can we have a carboxylate to the other side of this R group, and then the other side of the carboxylate can connect to similar paddle wheels? And then we essentially start forming a two-dimensional layer, right? Why do we have to limit ourselves in this particular unit? The other dimension, which is this L group, is expected to be electronically neutral because the charge balance happens because of the carboxylate and the metal ion. But this L can also be bidentate. It doesn't have to be a monodentate group. So essentially what I mean by that is, instead of choosing an acetate, let's say we chose a terephthalic acid or a terephthalate unit, which is this benzene dicarboxylate, and this kind of forms this two-dimensional network, and you choose DAPCO, which is this bidentate group, and it starts growing in the third axis as well. So now if you can combine this idea, you end up getting a crystal structure which looks something like this. It is a metal organic framework. It has got three-dimensional periodicity. It is composed of two different ligands, and it forms this nice pillar-layered structure. I'm using this word pillar-layered structure because it's going to come back at some point later in the slides as well. So what I mean by pillar-layered structure is that it's got a pillaring group, it's got a layering group. So the layering one would be the terephthalate, which forms this two-dimensional layer, and the pillar one is the DAPCO unit, which grows in the third axis. Right? So this is a very, very common kind of architecture in the area of morphs. Forming pillar layer architectures has been one of the first examples where how morphs were formed, and still to date, it's one of the easiest way to form porous structures using this idea. In terms of application, there are actually plenty of applications. If you go to the literature of morphs and you just type any of these keywords, you'll end up getting a lot of papers, especially in the recent years. The more important ones where the field emerged was actually for gas storage and separation, but now they've actually started moving towards catalysis, which is quite exciting for to be working in this area and applying these materials for catalysis applications. But today's talk, I'll not focus on catalysis or storage, but I'll rather focus on energy storage as well as antiviral application. So just to give a kind of a big picture idea, and how do we narrow it down next. So when I'm going towards the application areas, there are going to be some key aspects to it. I'm going to keep on using the word functional morphs. And the functionality in MOFs actually again stems from this idea that we have got two different building units. So the functionality can come from either the ligand and the metal, which I mentioned at the beginning. If you have a fluorescent ligand or an organic group, you apply fluorescence properties to the MOF. You have magnetism if you have iron as the metal cation. But the other way to do it is if you have a guest molecule that is active in some sense. So people have used something like TCNQ, which is known to have some host guest chemistry. So if you can apply a guest molecule that is functional, you can also use functional morphs from this guest molecule as well. So this is all the three components of the building units can be functional, and the eventual structure can be functional as well. But this is about the story of the building units. But what people have now done or done over the years is you can actually look at morphs not as individual molecular level particles, but they are actually bulk powders that form. So they have grain boundaries, they have got crystal structures, they have got single crystals. So at the edge of the single crystal or at the grain boundary of any of these particles, you can actually start functionalizing these surfaces. So these surfaces can be functionalized with things like biomolecules. You can apply organic polymers into it. You can also apply some kind of hybrid materials. So you can start forming composite like materials which have got a surface which is active for something else, and it's got an internal structure which is very crystalline and is porous as well. So today's example, one of the examples is actually going to be based on this idea where we surface functionalize a metal organic framework. So at the beginning, I said that the building units have to be very symmetric, right? So I've just chosen a selection of organic ligands that have been reported in the literature. So when the field started to emerge, people started to work on the pyridyl kind of groups, which are electronically neutral ligands. Over the years, people have found that carboxylates bind well to all the transition metals. So carboxylates are actually the more popular choice. And recently, people have found that azolate-based systems are actually very good in binding certain metal ions. So azolate-based chemistry has also picked up over the years. And some of the people who have also looked at phosphonic based chemistry, they've also seen that these kind of organic groups are also very useful as organic ligands. Why I'm showing this slide and these examples is to highlight one fact that if you look at all the ligands shown over here, they're essentially very symmetric. There is no ligand that is very asymmetric. The donor groups are either at specific angles to each other. For example, in this one, it's like at 120 degrees from each other. And then this one, it's linear. This one, it's linear. These ones have got four directions to it. These ones also have got four directions to it. So none of these ligands are asymmetric. And these ligands are very popular to form long range periodic structures. So this idea of having symmetric building units is really, really important. And if there is one message that I would like you to take away today, is that the building units matter much more than the overall architecture or how you prepare the systems. Because this field has evolved from the field of zeolites, and people who are working on zeolites typically use hydrothermal or solvothermal based synthesis. So MOFs at the early stage were actually prepared in the same way. You just put everything together in an autoclave synthesize and just heat it up. You end up getting a crystal or a powder that is crystalline in nature, and you end up getting the framework that you like. But over the years, what people have seen is you can actually use any chemical synthesis method that's known in the literature. For example, people have now started using microwaves, mechanochemistry, electrochemistry for preparing all of these materials. So the thing that I wanted to highlight at this point is the synthesis is not that important. Once you know what you're looking for, whether you're looking for a crystal, whether you're looking for a powder, a thin film, once you define your morphology, the synthesis is not the hard bit. The harder bit is actually choosing the building units. So once you know what you want to look for, the focusing on the building units becomes the most important thing. So there's one another thing that I also wanted to highlight at this point is not all the morphs are stable. Some of them break down or they're not very robust in nature. In fact, a lot of crystal structures that were reported in the 90s actually were of this type, where you prepare the morph material, there are guest molecules loaded inside the morph. Once you remove the guest molecules, as you asked, because it's so low dense materials, they start breaking down. And once you put back some kind of solvent molecules, they go back to this original phase. So Susumu Kitagawa in Japan, he gave this nomenclature. All of us are familiar with the generations of mobile phones, 1G, 2G, 5G phones. So he gave this idea of 1G, 2G, and 3G morphs. So the first generation morph typically breaks down when the guest molecules are removed. The second generation morph is actually the more robust ones, where nothing happens to the structure. The guest molecule just goes out and comes back in, but the structure remains intact. The third one is the one that his group is quite excited about working is once you remove the guest molecule, the structure actually changes itself. So this is an example of something what happens in our bodies where it responds to a solvent or a guest molecules, and when you take or put the structure back to its original form, you need the guest molecules to go back to its original form. So this is kind of the three generations of morphs, which is very very popularly followed in the literature of metal organic frameworks. I'll just throw in some stats before I finish the broader introduction. At the moment, as of now, there are more than 1 lakh crystal structures known in the literature. And as you alluded to, the lowest density of these materials is zero point 0.1 gram per centimeter cube. Now, this is a number that not all of us appreciate directly. All of us know the density of water, right? It's 1 gram per centimeter cube, nearly 1 gram per centimeter cube. So this is almost 10 times lighter than that. And it still has a porosity that is 7,000 meters square per gram. So just to give this idea, or you might need a few seconds to absorb this idea, but this is kind of the underlying thought behind why these structures are so fascinating. And of course, the interest in this field has grown over the years. So this field was kind of discovered or known in the 1990s, but very little interest was there for the first 10, 15 years. But if you look at the last data for the last 10, 15 years, the y-axis is the number of publications per year in all journals. And as you can see in the last 5 years, there have been consistently over 10,000 papers every year. That's roughly about 30 to 40 papers every day, which is a lot of papers for one topic, right? So with this very broad introduction, I will quickly just touch upon one aspect, which is this idea of the Nobel Prize. So morphs are now going to be more popular because of Nobel Prize awarded to the three of them. So Richard Robson is the one who proposed this idea of morphs having porosity. His original publication that won him the prize was in 1989. Umar kind of formalized the term metal organic framework. So this paper in 1995 has metal organic framework in the title itself. So this is the very first paper where you will find metal organic framework written somewhere. Susumu Kitaga was the one who actually thought that these materials can be used for something. So what he did in his original work is he took a range of few metal organic frameworks. He tried to put some gas molecules inside them and tried to reversibly remove them. So he showed that the pores cannot be just idle. You can actually start using it for something. And that's where the idea that I was initially suggesting, that these materials were very useful for gas storage and separation, came from one of these publications at the beginning. So if again you don't have to remember everything or you have to follow everything, but if you have to just take the key ideas from this. So amongst the three, Robson kind of showed that pores can be created. Yagi kind of showed that the pores can be stabilized, and Kitagawa again showed that the pores can actually be utilized. They're not just there for the fun of it, right? So with this, I will now shift gears. I'll talk a bit more about how these materials can be applied in different areas or different applications. So the first application that I want to touch upon is for energy storage devices. And before I jump into why and how morphs can be useful, I'll spend a few seconds or a few minutes on developing this idea of why energy storage is important. I think all of us appreciate why energy storage is important. We all are consuming a lot of energy every day. But this is kind of this projection or a summary of the global energy that is being consumed over the years. Although we think that we have been using more energy since our growth or our aging, but over the years, if you look from 1970 to 2020, this is a report from British Petroleum. You can see there's a linear rise. So this is something that is all of us know. This is nothing surprising over here. But the key thing that is the bigger issue at the moment for all of us is all of this energy is actually coming from oil and coal, which is kind of the problem for us to address as researchers, as scientists, as people who are going to be living in this world for much longer time now. Because the renewable energy that is contributing to this global energy consumption is less than 5% or 10% in certain countries. And one of the reasons why, I think all of us know why, is because sun doesn't shine. Today there is no sunshine. So if you have a solar panel outside today, you're going to get very little energy. If we have wind, we are going to get pretty good energy today, but not on all days. So this is kind of a graphic that sums it up very nicely. So the top panel here is the wind power energy that is calculated from a plant in Netherlands. The middle panel in the red is the the output that is created from a solar panel in Boston, and the bottom panel is the data from the national grid in the UK. So what they did is they just lined them up together. The x-axis is time in hours. So essentially, none of them have any kind of relationship between them. So there's a big supply demand gap, right? You're not going to, all of us, when we go back from work, we want to switch the television on, we want to switch our laptops, charge our mobile phones. So there's going to be peak current required at a specific time, but the sun is not going to be out there at that time. There's not going to be guarantee that there's going to be wind. So we don't have equal supply and demand. There's a bit of a gap, and to fill this gap we actually need a lot of energy storage systems. And that is the reason why we are investing so heavily on battery technologies, supercapacitors, and any other battery technologies that can solve this kind of gap in between, right? Batteries are something that none of us are surprised about now. This is a topic that all of us are carrying with us. All of us have at least two batteries with us every moment nowadays. And again, this is a graphic that I think none of us needs to be explained to. This is just showing the amount of lithium ion energy that's going to be required over the next 5-10 years. And this is to show that it's not rising linearly, but it's rising exponentially. And one of the key things to take away from this is electricity is considered to be one of the cleanest sources of energies. So a lot of poor countries or developing countries are actually investing a lot on electrifying a lot of things. India has done electrification to a great extent. And the moment we have a lot of electrification, we need energy storage systems, because that's the only way we can conserve energy to ensure that it's not lost. So we need a lot of battery technologies, and this is important because lithium ion battery is the only technology at the moment that is fully commercialized. It's proven, it's completely safe, and it's in our pockets. So this is kind of a technology that's going to be in demand for a short while now. But the problem is not necessarily this or this. The problem is the availability of lithium. So if you just look at the Earth's crust and look at the amount of lithium that's present in it, it's actually one of the weakest elements in the periodic table. And it's not just lithium, but also cobalt. A lot of us are having Apple phones and laptops, and cobalt is one of the key cathode materials in such batteries. And cobalt is actually sitting next to lithium, so it's again not very available. So we have a problem here that's not very obvious in the market. If you just go to the market, there's batteries everywhere, but this is going to be a big problem in a few years time. And not just the availability in Earth's crust, the second problem is global distribution. So lithium mines are not there everywhere. In fact, in India, when we discovered something in Jammu very recently, there was a big news, and a lot of industries are interested in that. But until we understand how pure that lithium is, how easy it is to mine that, we still can't rely on that source. So we have to rely on lithium that comes from elsewhere. Cobalt is actually even a bigger problem. The majority of the cobalt is coming from this dark color thing that you see is coming from Congo, and Congo is a politically unstable country. So getting systematic supply of cobalt is actually a big global challenge, and that is why a lot of mobile phones and uh, other electronic devices that were using batteries during the COVID period suddenly had this shoot up in prices, because the supply chains were affected at that time. So this is kind of again explaining this problem a bit more, that if you are relying on elements that require us to be mining in another country, there's going to be some supply chain issues. So we have to have technologies which are more local, more indigenous, so that we don't have to worry about all of these problems. And this is where the post lithium ion space comes into the play. So this is a graphic a couple of years back. A few leading researchers working in the space of battery technologies sat together, and they kind of came up with this idea of what are the expected battery technologies to hit the market in the next 5 or 10 years. So what they saw is that lithium is currently on the top, but sodium and potassium, which have got very similar chemistries as lithium, they're expected to hit the market next. And then you have got multivalent batteries, something like aluminum, magnesium, zinc, calcium, all of those batteries. They're still in the R&D stage, they're not commercialized yet, but all of them can actually be very useful because they are much more abundant in Earth's crust. Sorry? Cluster based batteries also can come, but again we're looking at the elements at the moment. We're not looking at the how they're prepared or how we can stack them. But you're right, yeah, that can actually minimize a lot of losses. That's true. And on the left side is some lithium technologies such as lithium sulfur, lithium air, lithium oxygen. But all of these battery technologies on the left side are not going to be replacing our laptops and mobile phones, because these battery technologies have got very high energy densities, and they can only be used for things like aerospace, flying rockets, and things like that, where we actually have to worry about energy densities a lot more compared to our domestic applications. So the key thing that we have to look for is all of these technologies. And for the next few slides that I'm going to talk about is going to be about sodium ion batteries. And why sodium ion batteries is, of course, it is the next element after lithium in that group. But the more important thing, it's abundant. And if you talk to industry, why they're so interested in sodium ion batteries is because they actually say that if you have got a manufacturing setup that is producing a lithium ion battery, you just replace all the precursors or all the salts that you have for lithium with sodium, and you can still end up getting a battery that comes out of it. In fact, there are a couple of companies in China, something like CATL, they're actually doing, they have got this conveyor belts. They produce lithium batteries for 4 days of the week. For 2 days of the week, they produce sodium ion batteries on the same plant, and one day is kind of for the changeover. So you can actually replace the existing infrastructure. You don't need to make new infrastructure for sodium ion batteries. The second key benefit with using sodium ion batteries is, apart from abundance and slight cost saving for the electrode materials, the big cost saving actually comes from the current collector. I think a lot of us don't see or appreciate this enough. Is in a lithium ion battery, we need copper as the current collector, because if you use aluminum as the current collector at lower voltages, aluminum tends to form an alloy with lithium. So we cannot use aluminum as a current collector in lithium ion batteries. But copper is much more expensive than lithium. So if you can replace copper with aluminum in the case of sodium ion battery, we're actually saving 10% of the total cost of the battery just by changing the current collector. You're not even worried about the chemistry or what the electrode material is. We're just changing the current collector and we get 10% savings. So this is kind of one big benefit of using sodium ion batteries. And some of the startups and industries that are actually working on sodium ion batteries have suggested that, of course, sodium wouldn't have the same metrics, performance metrics as lithium ion batteries, but they're not that far. So if you look at this chart on different parameters, in terms of cycle life, actually sodium batteries are doing better. But in terms of power density and energy density, volumetric energy densities, they're actually not too bad compared to lithium ion batteries. So there is decent amount of interest why we want to explore this particular space. So I'm sure some of you would have studied electrochemistry or rechargeable batteries in your education time, but this is just a refresher of how a rechargeable battery works. So this is what is there in our pocket at the moment. We've got an anode material, which is typically a graphite. We've got a cathode material, which is typically a lead oxide. This is where cobalt comes into play that I was mentioning. So typically this is lithium cobalt oxide or some form of cobalt oxide with different transition metals. And in this process, at the moment, what it's shown is that the lithium ion is traveling from the anode, it is going towards the cathode, and the electron that is produced because of this oxidation is traveling through this external circuit. So once this external circuit is activated, you can actually derive energy out of it, and this is why you light your bulb there. When you're charging your battery, the directions are reversed. So the lithium now goes from the cathode to the anode, and the electron is now flowing through this external circuit because you are pumping in electrons into the battery. And this is recombined, and the lithium atoms sit between these graphite layers. Very simple, very easy. It works, it's been proven. But the problem is not translating lithium chemistry to sodium chemistry, is because lithium and sodium have got different sizes, they've got different kinetics. So you can imagine that if you put sodium over here, it's going to have sluggish kinetics, it's going to be much slower. It may not fit all of these cathode materials. But the bigger problem in actually sodium ion batteries, translating materials from lithium to sodium ion batteries, is not on the cathode side, but it's on the anode side. Can anyone remember what the lithium graphite composite or the structure is? LiC6. Perfect. Thank you. So in the case of LiC6, on the anode side, you actually get perfect lithium insertion. But when you have sodium in there, there is not possibility of having LiC6 or NaC6, but you end up getting NaC7, which is symmetrically not a good number. So that's why thermodynamically inserting sodium into graphite is really, really challenging. And that's why if you put all of these battery materials in a sodium cell, you end up getting very little capacities out of it. So the bigger challenge for sodium ion batteries is working on the side of anodes rather than on the side of cathodes, because you can replace lithium cobalt oxide with sodium cobalt oxide. It might work, but replacing something with graphite is a bit of a challenge at the moment, and that is why a lot of people are working on the side of anode in these materials. So this is where a slightly old chemistry comes into play. This is organic redox chemistry, right? So this chemistry was discovered at the same time as the groups of Goodenough and other people were working on in the 1980s. They showed that if you take polyacetylene, you take any kind of unsaturated polymers, you put it against lithium, you start getting some lithium ion insertion into those materials or those polymers. But why that chemistry fell behind is because the inorganic salts are so good or so efficient that none of the people who were working in the industry, Sony at that time, they were interested in this chemistry. But over the last 10-15 years, this interest has picked up again, because now we have realized that we don't need batteries to be compact. We don't need batteries to be compact for a windmill. We don't need batteries to be compact for a solar panel. We don't have issues about size and volumes. So we can actually make batteries that are much bulkier and bigger in nature. So all of the limitations that were associated with these chemistries have kind of been derailed, and we can start focusing on this chemistry. And organic chemistry is rich. Some of you who work or like organic chemistry would appreciate this idea, but also this idea that we can actually make flexible batteries only with organic electrodes. If you have got inorganic electrodes, it's really hard to make flexible batteries out of them, where the electrodes can be bent, twisted, whatever shape. But if you have got organic materials in your batteries or the electrodes, it's very easy to form these kind of soft materials, which can be used for, let's say, our hand wrist watches and things like that. So all of these technologies are possible with organic materials. Of course, there are limitations. These materials have a low dense, so the effective capacity, the energy density that we derive out of them is going to be lower. In lithium and sodium ion batteries, we use organic electrolytes. So if you have got an organic electrode, the possibility of forming a side reaction is much higher. And all of these active materials have got low electronic conductivity. So typically, we need to add a lot of conductive carbon or some conductive additive to ensure that the electronic conductivity is retained. Right? So there are some limitations, but from these benefits, if these benefits are not enough to convince you that these materials are important, you can look at this particular paper that came a few years back. So they showed in the proof of concept studies, they just took waste plastic bottles, they converted waste plastic bottles into sodium terephthalate, and they just put sodium terephthalate to cycle against both lithium and sodium. And they found that you actually start getting capacities that are reasonably same as you would expect for a pristine material, which is this idea of recycling commercial waste. Because PET bottles are everywhere, it's here, it's everywhere around us. If you can find a way to recycle PET bottles into some functional molecule, we don't care about the size and the energy densities that we derive out of it. But if we can make a battery out of it, that would be quite a cool thing already. So this is this idea where organic redox comes into play or is featured very prominently. And if you're wondering how this electrochemistry works, this is kind of this paper from Tarascon's group in 2009, where they showed that if you have an alkali, dialkali terephthalate, in this case they chose lithium salt, and you have ion and electron insertion, you can actually have the insertion at this carbonyl site, and the double bonds kind of rearrange themselves to ensure that the aromatic nature is not lost. And the moment this ion comes out of the system, it goes back to its original form. And this chemistry works the same way for lithium, sodium, and potassium. And there is no kind of difference in the performance or the reversibility of all of these molecules. So, very simple chemistry. If you remember your preliminary organic textbooks, you had this keto enol tautomerism. It looks very similar to that, but it's just that it's associated now with an insertion of ion and not necessarily only this formation of an enol group. So, very basic, simple chemistry. But this kind of molecules, if you talk to an organic chemist, what they would say is that this is an organic salt. Typically, everyone in the literature calls this an organic salt. You've got sodium terephthalate, you've got lithium terephthalate, potassium terephthalate. All of us refer to it as an organic salt. But these organic salts are actually very important if you're a morph chemist. This is a good example for it. So, to prepare this particular morph, which is called as MIL 53, it is made up of aluminium. You start taking terephthalic acid, you treat it with some form salt of aluminium, and you end up getting this particular structure. Now, if you look at the solubilities of the precursors, aluminum nitrate is soluble in water, it's soluble in organic solvents, but this particular molecule is not going to be soluble in water. It would need some kind of polar organic molecule. So, to carry out the synthesis, you need to either do it at very high temperatures in water, where some form of mixing happens, or you have to use an organic solvent. But the moment you start preparing this organic salt, you can actually start carrying out the synthesis in water directly itself, because now this salt is going to be fully soluble in water. It's going to produce this MOF at room temperature. You don't need the energy input. So this is one way to produce green synthesis or do green synthesis of MOF by just changing the nature of the precursor. But why I'm showing this particular slide is we know the crystal structure of this. We know what aluminum nitrate looks like. But have you ever wondered how this looks like? So if you go back to the literature and we kind of just explore what this looks like, there have been some really good work done in terms of crystallography around this period by this group and a few other groups as well. And what they did is they just took this kind of carboxylic acid, treated it with lithium hydroxide, sodium hydroxide, potassium hydroxide, prepared these organic salts, and then just looked at the single crystal structure. And what they found is that this kind of forms in this particular structure. It's got this terephthalate groups over here, it's got a sodium oxygen layer, and it's alternating. Now try and recollect this with the introduction slides that I showed. This looks very familiar. It looks like a pillar layered structure. It's got a pillar in the form of terephthalate. It's got a layer which is of the sodium oxygen layer, and it's alternating. So it's almost perfectly three-dimensional morph-like structure, which is based on purely ionic bonds. It's got very little covalent character. It doesn't have a transition metal, so it doesn't have a coordination bond, but it's got good ionic bonding happening between the precursors. And this particular structure is not limited to this specific molecule. In fact, if you change it from BDC, if you make it biphenyl dicarboxylate, it forms the same structure again. And why these structures are important is in this particular structure, you have got a sodium oxygen layer. So now, if you can think of it as an active molecule for a battery material, the sodium ions can actually diffuse easily into this particular layer and carry out the redox activity there. So this is an example to show that if you take biphenyl dicarboxylate, the sodium version, and you put it into a sodium battery, you get very stable cycling over 150 cycles. Metal thiolates, another good example of this perfectly. Yes. So all of these molecules are like this morph like structures, and this is an example to show that they can be very useful battery materials as well. So if you're thinking in terms of the research areas where this field has been explored so far, there have been four different avenues. It is essentially true for any materials chemistry research, right? You want to work a bit more on the exploratory side. You go to the whiteboard, start drawing molecules. You want to figure out which is the active molecule, which is the active group. But in this specific example, let's say organic anode materials for sodium ion batteries, people want to know what redox chemistries work. You want to focus on synthesis and making it greener, not necessarily for publications alone, but because you want to make these materials more industrially relevant. So the moment you have green scalable synthesis, the industry people are going to be attracted to that particular aspect. So you also want to work in that area. Of course, if you're a fundamental chemist or a fundamental scientist, you want to know the mechanism really well. So you have to understand the all the features of the molecule and how the ion insertion happens. And of course, you always want to improve the performance, be it forming composites, be it forming something else. So these are typically the four aspects, as I see it, for any materials chemistry research, which when you're starting as a synthetic chemist or a synthetic experimentalist rather, you would rather want to focus on any of these four areas. So for the next few slides, what I'll do is I'll focus a bit more on the greener aspect, the greener synthesis aspect, and then come back to this area after that, a bit more about new chemistries. So this is kind of one subsection that's coming up next, which is about this greener synthesis of battery materials, right? So I was talking about sodium carboxylates, and I said that people have been taking dicarboxylic acid, treating it with sodium hydroxide, end up getting sodium carboxylate. This has been the synthesis in the literature for years. Even if you go back 50, 60, 100 years, you'll find people using the same synthesis method. You take a carboxylic acid, treat it with sodium hydroxide, you end up getting this. Now you show the synthesis to an industry person and they'll find a lot of flaws in this. The first flaw is you need a lot of solvents for this. both during the synthesis as well as the workup. Once you produce the material, you have to wash it using multiple rounds of solvents. So you're producing a lot of waste over here. The second problem is some of these reactions can take much longer time. So if you have to prepare a kilogram a ton of this material, you're not going to prepare this in 1 hour or 15 minutes. You need to keep it longer batch scale reactions. It's going to consume a lot of energy. So this is never an attractive method of producing any material, be alone a battery material. So this is kind of a big no. But what people can do is people can look at greener synthesis method. Two synthesis methods that I'll focus on today is mechanochemistry and microwave synthesis. Both of them fall under this umbrella of green synthesis, right? And both of them have got their own benefits. So, for example, if you look at mechanochemistry, typically we don't need any solvent. It's going to be very, very little. It's going to be actually the amount of solvent that we need for mechanochemistry is essentially just to ensure that we form a paste. And for those who might not be very familiar with mechanochemistry, it is just a mechanized version of how we produce masala at home. We just mix our precursors, spices together, we churn it together, and we produce the masala, which we add to our curries, right? So this is the same thing in a more mechanized or a more reproducible manner. So that is why we need to have mechanochemistry. Microwave synthesis, I'm sure everyone has seen a microwave somewhere, right? But instead of using a kitchen microwave, this is kind of a more formalized way to produce microwaves. In fact, you can use microwave heating in a floor synthesis as well. So you have continuous production of the material by using microwave synthesis. But the more important thing for this particular kind of synthesis is you can actually use both of these synthesis methods for any of the precursors. So none of these precursors are kind of absent to any of those forces. So, for example, you have sodium hydroxide, you have dicarboxylate. You take any solvent, you take water, ethanol, methanol. Any of those solvents are microwave active, so you can actually do the synthesis in microwave chemistry as well. So what I'll do now is I'll first focus on microwave, quickly focus on the how we can apply them, and then go to the mechanochemical synthesis. So for the microwave synthesis, this is a good example to start with, where you take naphthalene dicarboxylate, the pillar layered structure strikes back again, right? It's got the same structure. It's got the similar electrochemistry as sodium terephthalate. But the difference here is you can actually produce this material using microwave heating, and more importantly, the final material that is produced has got these chunky particles, and it's got like nice morphology that can be produced. The beauty with microwave chemistry is you can actually tune the frequency, you can tune the heating time, you can tune the temperature and other parameters, and you can actually play around with the morphology. So if your desired application has a specific morphology or a size of the particle that is required, you can actually tune it with the microwave chemistry. And this particular synthesis can actually be applied to a few other molecules as well. So if you can use the same protocol as here, you can actually produce the active materials or the sodium terephthalate and the sodium biphenyl dicarboxylate in the same manner. And this is to show that if you record a powder XRD pattern of them, you don't see any peaks corresponding to the precursors or any of the side products that may form in this particular synthesis, right? One benefit with using organic electrodes is actually you can use water soluble binders. There's one thing that I didn't touch upon much in my introduction is typically in our battery materials we use PVDF as a binder. The binder can be from, let's say, 1% to 5% to 10%, and typically that is to ensure that your active material sticks to the current collector and all of that doesn't fall apart when the ion insertion is happening. But PVDF is only soluble in NMP or any high boiling organic solvent. So if you have to produce a battery on a commercial grade, you have to use a lot of organic solvents, which is again a big no-no. But if you're using organic materials, you can actually start producing these batteries using water soluble binders. And in this example, there are two binders. One of them is a cellulose based CMC binder, and the other one is sodium alginate. And sodium alginate is essentially algae that we see everywhere around us. So it is essentially a very purified version of algae, and you get sodium alginate out of it. So in this example, the previous molecule, naphthalene dicarboxylate, was tested against both CMC and sodium alginate, and it was found that CMC works as a better binder. But the more important thing is when you're preparing a material using new synthesis, you want to benchmark it against its original performance. So if you take this material, cycle it 400 cycles, at a current density of 25 milliamps per gram, you end up getting capacities that are not dropping. And the other key thing to take away is the Coulombic efficiency. So Coulombic efficiency is the measure of how reversible ion insertion is. So if you're putting in one lithium ion, are you getting one lithium ion out of that structure? Or is it some fraction of it? So if you're getting 100% Coulombic efficiency, that is a good signature that this material is able to perform this ion insertion in a reversible manner. The other experiment is slightly different. You can imagine this experiment to be something that you're driving an electric vehicle or electric bike, and you suddenly want to accelerate. So you are actually demanding a lot more power from the battery. Then you apply your brakes, you're actually reducing the power output from your battery. So this is an experiment where we kind of change the electron, the current density that we apply to this battery, and check the capacities that the material is able to achieve. So in this case, we start with low current densities, we go up to higher current densities, and then we suddenly go back to lower current densities. So upon lowering the current densities, if you are able to get the same amount of capacities that we had at the beginning, this is a good battery material. So this is an experiment just to show that this is actually validating that particular experiment, right? The other key thing when you are actually producing a new material is to look at current voltage profiles, right? We all know or have seen it before. This is slightly different. On the y-axis, it's got a potential, but instead of current on the x-axis, it is showing capacities. But in this particular example, the mechanism that I showed, that the ion insertion happens at the carbonyl site. If it was happening at some other site, you would start seeing extra peaks appearing in this voltage trace. The reason that you're not seeing any extra peaks over here, that is a good signature that this synthesis has happened in a clean manner. So this is another experiment that kind of is a good way to prove that your synthesis is working fine, even when you put it into a battery at different current densities. Right? So with this, I will quickly touch upon this idea of mechanochemical synthesis. So mechanochemical synthesis, I said that you don't need solvents for it, right? So instead of using sodium hydroxide, you can actually start using even more environmentally friendly precursors. You can start using a weak base such as sodium acetate. And the reason for it is you don't really have to worry about heating it up. You don't have to worry about putting external forces. Shaking or mechanical forces are just enough to carry out the synthesis. So what can be shown over here, if you take dicarboxylic acid, you treat it with sodium acetate, you just ball mill it for specified period of time, you end up getting the sodium carboxylate of interest. And in this case, you can vary a few different things. You can vary the frequency of shaking. You can actually change the time. You can, of course, this is the obvious one, you change the metal ligand ratio, but you also can change the eta value. So for those who are not very familiar with mechanochemistry, eta value is the value of the amount of liquid per solid material. So what I mean by that is if you do all the calculations for everything that is put together in a jar, if we know the amount of liquid that we are inputting, if the liquid value is, let's say, 0.5 microliters per mg of the solid material, that would be classified as a solid state synthesis. If the number crosses that, it is classified as a slurry based or a solution based synthesis. So this is just a formal conventional definition that if you're looking for a solid state synthesis, a classic solid state synthesis, this eta value matters a lot, right? So this is just based on the amount of liquid and the solid that you have got in your reaction. So to perform the synthesis or to explore the synthesis, you can actually choose a range of molecules. In this particular case study, 4 molecules were chosen, all of them linear, no complications involved here, slight differences. So you go from benzene to pyridine, have the extra nitrogen side, you increase the length with BPDC, you increase the length even more with stilbene and have an extra conjugation there. More the conjugation, the better it is because it helps with electronic conductivity, but it also helps sometimes with ion diffusion. So the length actually matters a lot with these kind of materials. So I'm not going to bore you with the results for all the molecules, but what I'll do is I'll just show you how do we characterize it and test it. So again, powered XRD is of course the very basic experiment to see that the precursors are not left in the material that we obtain, and we're also not getting any side products during the synthesis. So these are the two key things that we always take away from such experiments. But when we put it into cycling, what we can see is that this material is actually even better compared to the microwave material, and it's actually performing, having much higher capacities. The capacities are on the y-axis compared to the previous material. And again, the rate performance, where we change the current densities over a period, is actually pretty okay as well. Why I'm showing this and why I'm kind of comparing it with the microwave is, I said with microwave we can tune the morphology, but with the ball mill we can actually reduce the particle sizes. And you can think of battery as an application where particle sizes play a very crucial role, because you want the ion diffusion to happen at every possible active site. And the way to reach or access every possible active size is to reduce the particle sizes in a controlled manner. Of course, you don't want to crush it and make it amorphous, but you want to ensure that the particle sizes are small enough so that you get very good capacities, and you can do such kind of experiments even at very high current densities. Right? Ball milling, is it the friction that actually? It is a friction and the local heating that is caused by the friction. So that's actually a good point, because there is no quantification of the amount of heat that is produced during the synthesis, but there are thermal maps which show that there is some heat that is evolved during the because of the friction. But so that will generate abnormal shape and size of particles. Yes, yes. So that is kind of the thing that you kind of optimize it. You have to work around the frequencies of the milling, the sizes of the balls, and of course the particle sizes you start with. So if you know all of that, you can actually work around it, and you can end up getting particles that are very uniform in nature. Right. Uh, so with this, I hope I've been able to demonstrate to you that organic electrode materials are not bad. They can be actually useful battery materials, and you can actually use these greener synthesis methods for producing them. So if you're looking at the molecules that I've shown so far, if you just keep on extending the length, you get same redox chemistries. There is no surprises there. But there is one molecule in the literature that looks fairly similar to stilbene, which is this azobenzene dicarboxylate. It's of interest because it's got different redox chemistries, it's got different cycling stabilities, it's different to the other molecules, but more importantly, it's got a voltage that is very different to the other molecules. So the other molecules, if you remember when I was showing the example for naphthalene, it had a voltage roughly around zero point 0.5 volts versus sodium. But in the case of azobenzene, this voltage is now much higher. It's now closer to 1.2 volts versus sodium. And why this is important is, if you're looking at battery applications where you have to tune the working voltage, this molecule can be a very important or a useful molecule to just mix it with something to either lift it up or change the working voltage. So again, these kind of chemistries are really, really important. But then if you have followed the talk so far, if you have understood what MOFs are, you've understood what sodium carboxylates are, you can start appreciating this idea. So instead of using this as an isolated molecule, why don't we use this as an organic ligand in a MOF material? The azo group is active. The azo group can be the redox active site inside a MOF. The carboxylates can bind to some transition metal. It forms this nice MOF structure, which is perfectly porous, and this azo group is now able to perform this redox chemistry. Does it work? We'll find out. So this is part of the next segment where I talk a bit about azo-functionalized MOFs. But before I jump into the exact results for this, I just wanted to highlight one more thing. Is in the area of MOFs, uh, in general, this is not just this particular case. There are two or three different ways by which we can produce battery materials or capacitor materials. One of them is we just use the pristine material, which are very few examples. Uh, the reason for it is the electronic conductivity is much lower. And the electronic conductivity is lower because the moment you have got porosity, all the functional groups are now apart from each other. So there is very little contact for the electron to hop or travel. So you're going to get struggle to get good electronic conductivity with highly porous systems, right? So the more popular choice is you just make a MOF, burn it, obtain carbon out of it. The carbon might have metal nanoparticles inside it, and use this particular thing for supercapacitors, for batteries, and other things. So this is kind of the more popular route. But I said that the pristine MOFs have been used in the past, and one of the first examples was this MIL 53 iron, where they used this iron redox from plus 2 to plus 3 to insert lithium ions. The other example came from this group in 2014, where they took a copper based MOF, and this redox chemistry of copper 1 to copper 2 was utilized to insert sodium ions. Right. So coming back to this idea, whether we can use azo based systems, right? And what the morph that we can use, or any morph that has to be used for such applications, has to be chemically resilient. It has to withstand constant ion diffusion. And one of the popular families of morphs is this zirconium based morphs. And why is that so? Because zirconium plus 4 is a hard cation. It has a strong coordination bond with oxygen donor ligands. So typically, if you form a zirconium based carboxylate kind of structure, it's going to show very high chemical resistance. It's known to have resistance to different pH conditions. It's thermally stable as well as it's got this other properties of porosity, functionality, and other things. So if you produce this particular cluster of zirconium oxygen, this is going to be very very stable. So if you have to go to the lab and prepare a morph, and you don't know where to start with transition metal, if you know your ligand donor is carboxylate, a good choice would be zirconium. Just start with zirconium. You're more likely to get a very stable system. So the other feature with zirconium morphs is the morphologies are really beautiful. So this is the SEM image for that morph that I showed in the previous slide. It's a nice octahedral shaped crystallite, right? It's really very pretty. But the more important thing, if you're looking at for a battery application, is once you know the morphology of the particle, you can actually track that morphology. Because the moment you put it onto a current collector or something, and if you're tracking this battery over a period of time, once you know the morphology of your starting material or the active material, you can actually keep tracking that particular morphology to see if there are any changes happening in that. Right? This particular morph is again super porous. It's got close to 3000 meters square per gram porosity. It's very, very low dense and very porous as well. But the more important thing is it shows azo redox. So the redox activity that is corresponding to this group at 1.2 volts versus sodium is pretty much active over there. And the benefit of using a porous system or a morph like material is shown in this particular graph. So if we cycle this material over 150 cycles, we actually see no drop in capacities. So if you have porosity, the ion can easily diffuse. The functional group is away from the coordination bond, so the coordination bond is not disturbed at all. The activity that happens is happening inside the pore, or on the part of the ligand is inside the pore. So it's completely smooth. There is no drop in the Coulombic efficiencies. So this is all very clean redox activities. We can track this insertion mechanism by a few different ways. You can start looking at it from solid state NMR, where you look at sodium NMR and you compare the sodium NMR from the first discharge. First discharge would be the point where you insert sodium into the system. So this would be very different from just the blank sample. You see this extra peak appearing over here. The moment you take sodium out of the system, you start seeing this go back to its original shape or size. I'm not an NMR expert, but I can tell you that this looks different. So you can start tracking all of these sort of processes using such solid state characterization. The other characterization that you can use is you can stop your cells at point of complete sodiation. So the point green would be complete sodiation, point purple would be complete desodiation, and you can collect Raman data and you can start analyzing it. The plot on the top is just XRD patterns. It is to show that the crystal structure is not changing, or it is not moving or shifting to some other point, but it is stable and intact. But the key thing that changes are happening in the Raman spectra. There are two peaks, roughly around 900 and around 1200 centimeter inverse, that actually reduce the intensity when the sodiation is happening, and they come back to its intensity when the desodiation is happening. And to understand this, what you can do is you can take help from theoretical groups, and you can do some DFT calculations to understand which stretching frequency is getting affected. So in this particular example, the key stretching frequency is the azo group, NN double bond. But the NN double bond is actually masked by the carbon. So we are adding conductive carbon over here. Conductive carbon has got D and G bands. Those hide the azo bond stretching. So what you can do is you can start looking at some other bands. So in this particular case, this particular band, which is the CN stretching, appears at the same region as this particular peaks. So the idea is that if your azo group is participating in the redox activity, the sodium is going to go and sit next to this azo group, and it's going to block or reduce the intensity of this stretching. The peak that you get associated with this stretching is now going to minimize. The moment the sodium goes out of the structure, this bond is now free to stretch again, and you start seeing this particular peak appear again. So this is a map just to get out as an output from the theoretical calculations. But if you compare this output to your experimental data, you can actually map it up nicely, and you can say that this is actually the point where, or this is actually the point where the ion insertion has completed at the as a group, right? So this is the kind of the summary of my second part, which is I hope I've been able to show you that azo-based chemistry is quite attractive, and if you have a morph system, it is actually even better, because then you have got a porous structure where ions can diffuse easily inside the system, come out easily, and you don't have to worry about sluggish kinetics and other things. At this point, in the last 15 minutes, I just changed tracks to a completely different area of application, which is about using morphs for tackling viruses, right? Uh, this is kind of the schematic which encompasses what I'm going to talk about. So this is a long figure showing multiple layers of morphs, and it's got this kind of spiral groups coming out of the surface. And this is where the story goes next. But before I go to the story, a bit of a background, of course. uh, all of us have lived through COVID 19. So I think there was this tweet today morning saying that today is the sixth anniversary of the first person in Wuhan getting detected. So it's been 6 years. Yeah, it's been 6 years. But this is an example from 2006 where people wrote this review in Science, and what they said at that time, there was MERS, there was SARS-CoV-1 that had happened, and what they said is, if any such kind of pandemic happens in the future, the first thing that you should do is everyone should start wearing masks, they should start wearing respiratory protection, and all the workplaces should have air filters. This is the first outcome from 2006. So if you think that everything happened in 2019, no, it's way back in time. And at that time, people did a lot of other studies as well. So this is again before COVID-19 2017 paper, where they just took different mask materials, uh, did physical separation based on particle sizes. So you just spray particles of different sizes and you try and filter them and calculate the efficiency. Of course, we know that N95s are really good. Cloth masks have got very limited sieving effect. But the key thing to take away from here is that all of this data is available with us, but the thing that is missing from here is they're not kind of programmed for specific particles. This is just physical particles. This is usually done like a sodium chloride aerosol. You just inject sodium chloride aerosols through all of these materials, and you end up getting this efficiency. But during COVID 19, a lot of people suggested that we start using silk as a cloth. And the reason for using silk is that it has got electrostatic layers. The moment you have got electrostatics on the surface, the virus particle is going to die by itself. And that is the idea that people started using or suggested to use silk until we had proper vaccines and drugs and everything. But if you look at the available choices of cloth materials in our home or in our wardrobe, we cannot start using everything because some of them are going to compromise on breathability. So if we start wearing silk, we are not going to breathe. We are going to struggle to breathe. So cotton is of course the favorite choice. It's a good breathable material. But now, if you have learned about morphs, so morphs can actually be very useful for such applications, right? Because they're very porous, they don't compromise on breathability. So the first aspect for porous materials is they're useful for such kind of applications. The other thing that I want to highlight at this point is the sizes. I said sizes in my graphic over here, but this is an elementary school textbook. All of us have seen this, right? So we know that bacteria are somewhere over here, which is 1 micrometer. We can start seeing particles that are bigger than bacteria using naked eyes. Things that are smaller than bacteria are hard to see using optical microscope. You need electron microscopes. And the power of electron microscopes was actually revealed during COVID 19, when literally within 1 month of this virus or epidemic hitting, we had a TM image. And this TM image came in this paper in March 2020, in this medicine paper, where they actually looked at a COVID particle. They found out that the COVID particle is from 60 to 140 nanometer wide, and the spike protein that all of us are familiar with is actually just 9 to 12 nanometers long. So this is the power of kind of the electron microscopy now that we are heading towards. And this is an image that all of us have seen thousands of times. I'm not going to describe it anymore. But the thing that I wanted to highlight here is, if you talk to a person who works on drugs and vaccines, they'll tell you that they don't look at this particle, what's inside. Of course, they want to know what's inside, because the yellow part over here, the spiral thing, is the viral RNA. So once this COVID particle sticks to a human cell, this viral RNA is actually going to infect you. not the one that is outside. But the one on the outside, which is this pink spike protein, is the one that is responsible for binding to human cells. So if you don't have this particular thing, it's not going to bind to our human cells, right? But the way drug people working in drugs and vaccines do is they either trick our human cells with something to show that you have got a spike protein in our body. So drug molecules are typically uh, inactive virus particles. So they just trick our cells to think that you have to now fight against this. So you kind of prepare antibodies that can react to that. Or you can have vaccines that just block the spike proteins. So you just ensure that the spike protein somehow doesn't react our human cells. And why this is so important is if you look at all the diseases, I appreciate that this is not very visible, but if you look at all the diseases of the same family, could be SARS-CoV-1, MERS, and other families, they all have similar structures. So the part in blue is the part that is inside. It's going from here to there. And the part in the pink and the greens is the spike protein. So if you are able to devise a strategy or a mechanism by which you are able to focus your attention on this part, you can actually start making drugs and vaccines that can apply to different viruses and any of these families, infections caused by viruses in any of these families, right? So it's again very important to look at COVID-19 from or viruses from this particular aspect. In terms of sizes, we have learned about morphs today, and I said that morphs have got a pore size, they're quite porous. But what is the actual size? So typically, morphs have a pore size which is roughly 2 nanometers or 20 angstrom. A spike protein of the virus is 9 to 12 nanometers. So there is no correlation. There is no way a spike protein is going to sit inside the pore of the morph. That is too big. The virus particle itself is much bigger. It's 60 to 140 nanometer wider. So again, it's a bit pointless to worry about what morph pore sizes are. But the key thing where morphs can play a role is the actual particle sizes. So when you produce morph particles, they typically are from 20 nanometers to 2 micrometers, and this window is perfectly suitable for interacting with the virus. Of course, it's going to be much bigger than the spike protein, so you can actually have the entire spike protein interacting with the morph surface, right? But in principle or in air, we don't get the virus floating by itself. It is enveloped by water or moisture molecules. So it is forwarded as a aerosol particle, not a separate isolated virus particle. So remember those times when people told us when you're coughing, sneezing, be away from someone. The sneezing and coughing is actually producing this aerosol. It is not producing this. This is already there. It is just ensuring that this is transported well. So the moment you have things which are having water around it, it's going to carry it much faster. So this is kind of the size chart where morph can play a role or be part of it, right? And this is an image that I showed in my introduction slide. So now you can look at the morph surface. You can functionalize it in some way, and that surface functional group can interact with the virus now, right? It's getting there. The story is building up. So this is the idea. You just have some form of external functionalization to ensure that the spike protein sticks to the morph particle and it doesn't move further, right? But we don't just want it to just stick to it. We want it to be inactivated. So how do we do that? So if you look at like very old literature, this is a paper from 1962, and at that time there were no electron microscopes, no sophisticated techniques. But what they showed is that you take any virus particle, just dehydrate the virus particle, it dies because it needs water for its survival. So you need really high humidity. So Chennai weather is not good for such kind of viruses to die automatically. But if you go to, let's say, a drier place, it's more likely to dry by itself because it needs water for its survival. In fact, this was an example or a study done by a group in IIT Bombay, a physics group, where they looked at the survivability of COVID-19 particles on porous surfaces versus impermeable surfaces. And what they showed is that if you're coughing and if the particle goes onto a wooden surface, it has a greater chance of dying early than if you cough on a metal surface. So again, people used to tell us that if you've got metal rods in buses and on the walkways, on the staircases, don't touch those metal part because the particle is still alive because it's water there. It's not dehydrating fast enough. But if you've got wood, it's going to start dehydrating much faster. It's simple physics. So if you're interested, you can have a look at this particular paper. So what you can do, you've got a morph particle, you've got the external surface that binds to the spike protein. You've got this idea that dehydration helps to kill it or inactivate it. Why not combine it together? Have a hydrophilic pore So the internal pore of the morph can be used for dehydrating, and the external surface can be used for binding it to the spike protein, right? So I'll just combine this together into this story. So you've got the morph particle, the external surface is now functionalized with something. This external functionalization binds to the spike protein. You've got the internal pores that are empty, that are hydrophilic in nature. So the moment it is stuck to the surface, you ensure that the internal pores are able to dehydrate it, and then the particle is completely inactive, right? And the way you can do it is by any choice of morphs essentially. But again, zirconium morphs are favorite, right? Because they're very stable, they're chemically resilient. So you can choose a family of these morphs. In this particular case study that I'm going to show, it's the three families. One of them doesn't have any secondary functional group. One of them has got this amine group, and the other one has got a nitro group. And this is with the idea to see what these groups have got to do with this internal functionalization in terms of water adsorption properties, right? So all good said and done that you need something to functionalize the surface. But what do you functionalize it with? So this is where the power of computational chemistry comes into play. At the time when COVID hit, a lot of papers, if you go back to that literature, there are hundreds and thousands of papers coming from theoretical groups or computational groups rather, where they just took old drug molecules that were known in the literature, FDA approved, that were not used at the market. And what they did is they just took those drug molecules, took the spike protein or the virus particles, calculated the binding energies. So wherever they found that there's a good hit, and if that drug molecule is still okay for human consumption, that drug was repurposed for clinical trials. And this is how you typically do it, but at that time it was much faster because of computational chemistry. So being a morph chemist, it always is attractive to see carboxylate groups. So carboxylates and phosphonate groups are very nice in that sense that they bind well to transition metals. So these three drug molecules, folic acid, nystatin, tenofovir, they were found to have good binding ability to the spike protein of the virus, and they also have these functional groups where you can bind it to the transition metal. So the idea is you just take these three drug molecules, tag it to the surface using coordination bonding, and you have got amine and nitro in the internal part that takes care of the hydrophilicity. Right? So the first part is to understand whether the internal pores are hydrophilic or not. And you can start seeing that the moment you have got different functional groups. So the one in the black graphs are the pristine morphs. The one in the red are the one functionalized with folic acid or Fa, and the one with the blue are the tenofovir functionalized ones. So tenofovir is the smallest molecule. Folic acid is this long chain molecule. So in case of the folic acid, actually the capacity of absorbing water is not changing much over the three morphs. So the left one is pristine morph, the one in the middle is the amine functionalized, and the one in the corner is nitro functionalized. So in the case of the three, the folic acid one doesn't do any harm. The tenofovir one actually reduces the capacities of water adsorption, and this could happen because the molecule is small, so it is actually now blocking the pores. It is not letting the water molecules go inside the pores, but it is still showing some water capacity. So that is still not a bad thing to happen because we still want the internal pores to be somewhat hydrophilic. The next part, which you can of course have to study, is do some protein binding studies. And the protein binding studies can't really happen with virus particles by itself because they are either super expensive or they are really difficult to handle in regular labs. So what you can do is you can start working with analogs, and a simple analog is bovine serum albumin, which is available in regular biochemistry labs. You can just take those protein molecules and you start treating them with different morphs and their functional groups. So already we can see that one of the functional groups, nystatin, is not so good because it's having very poor binding capacity. But folic acid and tenofovir have got good protein binding capacities. So they pass the first test. But then you actually tried with the spike protein of the virus. And when you treat it with the spike protein of the virus, you see that close to 90%, or in this case of folic acid, more than 95% of the protein is binding to the morph particles, which is ensuring that the first part of the strategy is working really well, so that we are not getting any remnant proteins that are left into the solution. So this part is kind of confirming that the hypothesis or the idea or the strategy is working in this particular case. But as material chemists, we just don't want to rely on that data. We also want to look at images. We like seeing electron microscopy images. So the one on the left panel is just this protein BSA. This is just the zoomed in version of this particular. It's got this flaky, thin crystalline shape crystallites. The one in the middle is the morph without any functional group treated with the protein. where you see that the dark images are for the morph, but you don't see any flaky things in that image anymore. The last one is the one which is functional group, which is now having the folic acid, and you check that image and you see that the flaky particles are now all around these particles. So that kind of suggests that all the BSA are now kind of surrounding the functionalized morph particles, which is again quite a good indicator that this original strategy is working. So taking this further, you don't want to work only on powders. You want to take it to some real world application. So what you can do is you can just take a cotton fabric or essentially a cotton like a film, and you start growing morphs on top of it. Once you go the morphs on top of it, you then functionalize the morphs using folic acid, and the color changes over here. This is a copper morph. It goes from blue to green. In the case it's above, it's the aluminum fumarate. It goes from white to yellow. And why this color change is important, especially in the bottom case, is the color change in copper happens when there is ionter distortion, right? So that indicates that the folic acid is actually binding to the copper and not binding or sitting at somewhere else. So this was a good indication to show that this is actually working as a strategy, that the folic acid is now going only on the surface. Of course, we can do basic protein binding studies, but the key thing to look at is actually the survivability of actual virus particles. So the ones on the left are any bright spot that you see in the left panel are virus particles that are active. You treated all of these solutions in different cases. This one is the plain cotton. This one is the morph without a functional group. This one is with the functional group. And you see that in the case of functional group, there are very few bright spots left. So that means the survivability of the virus particles after 30 minutes, if you put it on a fabric, is going to be very minimal. So this is kind of summarizing this idea that you essentially can functionalize morphs in this very specific manner and ensure that you can start killing viruses. Of course, this is proof of concept. This is very basic studies, but this is to show that these kind of systems can be used for different biomedical applications.
Was the mob binding happening with the any ligand molecule?
Yes.
Once they reach to the target site, how they release the folic acid to particular target site? Is there any mechanism?
No. So in this case, it was not thought of as a removal thing. It was thought of as a one-time use. But yeah, it's a good question. We can actually start thinking or coming up with ideas which can work that way. Yeah. So yeah, in the end, I would like to thank Professor Pradeep, Professor Rajneesh Kumar, and all the organizing team, and all the people who have worked with as collaborators. And thank you all for your attention.
Due to shortage of time, we will take only two questions.
So, sir, I want to ask about the azure-diazine carboxylate. So, if we think in terms of the structural stability, nitrogen bond should be equal in the steel beam like carbon.
Right.
So,
Right.
what is
Yeah. So in this case, because we're not doing any kind of harsh solution-based chemistry, we're just doing solid-state chemistry in principle.
temperature?
We're not heating them in a battery. We're not going to heat it, so we don't have to worry about temperatures. But yeah, you're right. If you're looking for just comparison between steel bean and azo, yeah, steel bean will be better.
Okay, and one more question. Though mom is really exciting, but it's been quite a while now that cough is taking over all the attention.
Yeah.
So, what's your take on that?
So coughs are exciting, of course. They're way more porous than moths are. Uh, the the kind of the limitation with coughs is that you have to build big organic molecules to ensure that you get more porosity and functionality. Those can be slightly more expensive. Whereas with moths, you can one part of your building units can be really cheap. I showed zirconium, that is not cheap, but like you can start working on things like iron and things like that. So the overall cost aspect can be slightly in favor of moths. But yeah, coughs have got very good applications.
Eliminating the metal that can be the one.
Yeah, yeah, but it depends upon the application, I would say. Because like for certain applications, you would need the metal to make it more robust or to have it slightly higher dense materials. Because coughs can be even lighter than this. So yeah, maybe it depends upon the application, I guess.
Thank you.
Sir, actually, this quick fundamental. In your slides, you show like whenever you convert carboxylate to carboxylate, that time you use like potassium hydroxide or sodium hydroxide.
Yeah.
At 150 degrees Celsius, you use methanol or ethanol. Why? Not other stuff. which was showing more boiling points.
Yeah. So the one reason is we don't want the solvents to stay in the system, right? Because this is going to be a solid material that comes out. So we want to dry off the material. If you are using a low boiling solvent, it typically is very easy to dry it off. If you are using high boiling solvents, of course it will form. It's not going to be a problem with that. It is mainly to ensure that we get rid of the solvents very easily. And if you've got a low boiling solvent, you can just use vacuum and a little bit of temperature compared to, let's say, DMF. If you're using DMF, it requires a lot more energy to remove the solvent.
That is the reason.
Yeah, because this was in microwave synthesis. So this was to ensure that we get high pressure. So methanol and ethanol is basically to ensure that it's low boiling, so that we get enough pressure. If we have DMF at 150 degrees, it is just about its boiling point. So it's not going to generate extra pressure into the tube. But at methanol, it's way above its boiling point. So it's going to generate a lot of pressure. So because of this pressure, you can actually carry out the synthesis much better.
In boil method, you use sodium acetate.
Right.
So how did you remove that sodium acetate? If you add excess.
Right. Good question. So we take carboxylic acid. We have got sodium acetate. So the byproduct that is going to form is going to be acetic acid. So acetic acid is again a low boiling thing. You just put it into the oven at 50, 60 degrees Celsius. It goes by itself. Or you can, if you want, you can apply some vacuum to it. It can dry off by itself. And if you want to characterize this, you can always use TGA and things like that to ensure there is no residual solvent left.
Usually morph is called as a polar conductors.
Yes.
Particularly in energy storage
Yes.
applications, we need more conductivity.
Yes.
Usually many of them go with the morph-based composites.
Right.
In order to synthesize a conducting morph, is there any particular type of ligand or liquor we
Yes.
should take, or particular metal type we have to take?
Yeah. So typically, you need the ligand to be conductive in that case.
Yeah.
So there's a family of conducting morphs, two-dimensional conducting morphs. They have got like this graphite-like architectures, where the porosity is now reduced in one axis, but the layers are now conducting. So there's nice possibility of electron transport, but it depends upon the choice of the ligands.